Hey everyone, and welcome back to the channel. Today, we're tackling LeetCode problem 37, Sudoku solver. This is a classic problem and a great way to understand backtracking algorithms. The goal is simple. You're given a partially filled 9x9 Sudoku board, and your task is to fill in the remaining empty cells to complete a valid Sudoku solution. Remember, a valid Sudoku solution has the following rules. Each row, each column, and each of the 9 3x3 subgrids must contain all digits from 1 to 9 without repetition. Sounds challenging? Don't worry, we'll break it down step by step. We'll explore different approaches, understand the nuances of Sudoku, and finally, implement a clean and efficient solution in Python. Let's dive in. Understanding with examples. Let's look at a couple of examples. Imagine a Sudoku board with a few numbers already filled in. We need to ensure that when we place a number, it doesn't violate the rules. No repeated numbers in any row, column, or 3x3 subgrid. Consider a scenario. If we put a 5 in a particular cell, and there's already a 5 in the same row or column, or within its 3x3 subgrid, that's an invalid move. We'll go through a couple of examples on the whiteboard showing how we can visually check for validity. Understanding these rules is key to building our solution. The next part is exciting, building that solution from scratch. Brute force approach. A brute force approach would involve trying every possible combination of numbers in the empty cells. For each cell, we'd iterate through numbers 1 to 9, checking if placing that number is valid. If valid, we continue to the next empty cell. If invalid, we backtrack and try a different number. However, this approach is terribly inefficient. Think about the number of possibilities. It's enormous, leading to exponential time complexity. This might work for smaller puzzles, but it'll quickly become intractable for larger or more complex ones. So, let's explore a more efficient and elegant solution. Optimal solution. The optimal approach leverages backtracking. Backtracking is a powerful technique that involves exploring potential solutions systematically. We'll start by finding the first empty cell. Then, we'll try placing numbers from 1 to 9 one by one. If a number is valid, we recursively call the function for the next empty cell. If we reach a point where no valid number can be placed, we backtrack, undo the last placement, and try a different number. This process continues until we find a solution or exhaust all possibilities. The key here is the efficient validation of number placement at each step, ensuring we don't waste time on invalid configurations. Code implementation. Let's see the code in Python. We'll define a function that takes the Sudoku board as input. This function will recursively explore the solution space using backtracking. We'll implement helper functions to check for row, column, and subgrid validity, ensuring that we don't violate the Sudoku rules. The code will be well commented so that each step is clear and understandable. We'll trace the execution through a few steps to see how the backtracking algorithm works its magic. Time and space complexity. Our backtracking solution has a time complexity that's hard to express precisely, but in the worst-case scenario, it can be thought of as O of 9 to the power of number of empty cells. This is because in the worst case, we might explore every possible number for each cell. The space complexity is mainly determined by the recursion depth, which is at most the number of empty cells. Therefore, the space complexity is linear with the number of empty cells. While not strictly polynomial, this backtracking approach is significantly faster than the brute force method. In practice, it solves most Sudokus quite efficiently. Engagement break. Before we wrap things up, I'd love to hear from you. If you found this explanation helpful, please give the video a thumbs up. And don't forget to subscribe to the channel for more LeetCode tutorials and algorithm walkthroughs. Let me know in the comments below if you'd like to see more problems solved using this technique, or if you have any questions about today's problem. Your support keeps me motivated to create more helpful content. Conclusion. So there you have it. We successfully solved a LeetCode Sudoku solver problem using backtracking. This problem highlights the power of backtracking